everyone. My name is Vinayak Vadlamani, and this is a talk on how we use Capella for the development of the robotic architecture using a robotic arm called Staark that was developed at Redwire Space Europe. In today's talk, we shall be talking about why we use Capella over other alternatives. What kind of a role does it play in robotic architecture development? And I'll show you through some examples and also walk you through Capella during the presentation. Thanks to Obeo and Thales for giving this opportunity to share this presentation, and I hope you can follow on. Yeah, so first off, a little bit about Staark. Staark is a robotic arm product, a subsystem really for space applications, which was developed by formerly known as Made in Space Europe, now called Redwire Space Europe, along with some expertise and help from the Luxembourg Space Agency. So it's a 6 degree of freedom robotic arm solution, which has control of a flight computer called a robotic control unit, which is this box that you see on the right side in the upper image. 6 embedded joints with almost 200 Newton meters of torque and a universal tool flange or an end effector. And also hold on and release mechanism. So these parts that protrude down are basically locks to secure during the launch with the spacecraft so that the robotic arm is secured. It also has the internal flight harness. And let me just play along a short video of a prototype of Staark. So this was during last year when this arm was tested, made with flight components. So we're doing some ground testing here, as you can see in the image, rotating certain joints in a certain configuration. And this robotic arm is used for mostly designed for on-orbit servicing, as well as in space manufacturing applications. And it has many features, including compliance control and partitioning control. And yeah, always fun to look at hardware when it's built, especially for space. These hardware are put through certain kinds of environmental testing, and this arm was also put through the same rigor of tests and has and is in space jargon is called a TRL6 qualified robotic arm, which is the maturity of the product. Yeah. So yeah, the robotic arm is part of a robotic architecture, and now we'll talk about that. But before that, a little bit about myself. I served as a chief systems engineer or lead systems engineer at Redwire Space Europe until recently, and now I'm an independent consultant for space systems engineering and model-based systems engineering. I have 12 years experience. My education has mostly been in aerospace engineering. Currently also trying to get a CSEP certification, and I'm primarily focused on the upstream space domain. So that means spacecraft and component engineering and manufacturing and testing. I also have some experience with critical verification and validation on the defense applications. And I've been using Capella or the Arcadia method and familiar with it since 2017. So it's been a while. And I've also tried to introduce some of these concepts in the companies where I've worked. My interests are, of course, space robotics, including autonomous applications, some verification and validation for spacecraft and spacecraft components, and formal verification techniques for autonomy agents. So, why MBSE for developing such products? So, we have built Staark independently as a product, but applications have come later. So, when we try to incorporate the usage or the operational architecture of a robotic arm, we have customers who want us to develop studies or architectural trade-offs. So as part of that, I'm using a stakeholder diagram by Jean-Luc Warren, one of the developers of the Arcadia method, and Capella from Thales. So here I mostly use Capella myself to understand and do need analysis. So operational need analysis, what does the system need to perform end to end? And sometimes I also use it to check the feasibility and the cost of requirements validation and verification, including testing and functional aspects. And I also have a team where we have functional analysts who do functional analysis or breakdown of higher level operations or needs, and for writing and flowing down requirements. For today's talk, in this example, we're going to take a very simple robotic architecture. And when we deal with architectures, um, another workflow that I wanted to use to explain how we use Capella and in model-based systems engineering is that as a chief systems engineer, it's my responsibility to use and define complexity of how many interfaces are involved, and sometimes also provide or commission new studies. For example, for robotics, sometimes we have to perform reachability analysis of a certain configuration, and also some other kinds of functional analysis. And then we have to define these definitions so that the customer can deem whether they have such interfaces and if they can comply against such a implementation of a robotic element in their architecture. At the end, the customer usually asks us for trade-offs between several architectures, including what kind of end effectors, what or tools to be placed at the end of the arm, what position should the arm be stored in, and what should be the reach of the arm and how many joints it should have. So we do that as part of a study using some sort of architectural model trade-off. So while trying to introduce the concept of robotic architectures, it's important to know some of the existing robotic servicing architectures. So on-orbit servicing really is a process or a field, a mission in which a robotic service element, usually a satellite carrying a robotic arm, goes to orbit. It approaches or rendezvous with an existing satellite on orbit, performs only either an inspection or performs some additional tasks, which may include uh, interfacing or manipulating a target, repairing or extending the life or mission by replacing some sort of block on the satellite or refueling. In other architectural needs, it might also need to carry the satellite to another graveyard orbit, which are called disposal operations. And then it returns back to its parking orbit originally. So this is, of course, from an organization which develops standards for on-orbit servicing. And this is an example taken from them. However, there are practical companies like Space Logistics who have already performed on-orbit servicing for commercial satellites, for example, the MEV-1 mission, if you'd like to look it up, and as well as for on-orbit servicing, as I mentioned, it's also used for in-space manufacturing. But for the purpose of this Capella model use case, we're going to focus on a robotics servicing application, which is capture and manipulation. So in the Arcadia method, it is very important to justify and use justify and define a system of interest. For this, we developed the system of interest after we've been through a couple of viewpoints in Capella. So system of interest for us in this scenario would be a robotic servicing system that has a spacecraft or a servicer, an operator, as well as a robotic arm and any services that the robotic arm may need or require during the mission. This use case that we intend to demo today does not use the last two layers of Capella, so we do only operational and system analysis because we analyze various architectures and then derive the trade-offs of how uh, these architectures would affect the overall impact of the mission, or the cost of the mission, or the return on the mission. So although the use case can extend to a physical or logical implementation, uh, today you'll not see that. So that's the intent of the analysis that we usually use for Staark. Okay, so the example concept of operations or ConOps, which is more like a storyboard, if you're familiar with requirements, is today we'll be just using an example, which is launching a satellite, launching the servicer along with the robotic arm, commissioning or making sure that the satellite and the robotics are working on the servicing satellite, deploying successfully and extending the arm on orbit, then hoping the satellite rendezvous with the target to the required distance and velocity, and then using the robotic arm to capture the target. So that sets the context for which we will today demonstrate how Capella can be used and the Arcadia method can be employed to see the impact of robotic arm on servicing architecture. Okay, moving on then. Now we come to the modeling part and the modeling bit. And for those who are familiar with Capella, they would know this as an operational entities breakdown model diagram. And so here we list all operational entities and actors uh, for this capability. So operational entities are the client or the servicer. This is not the spacecraft, but the entity that owns the spacecraft or operates the spacecraft. The spacecraft is called as abbreviated as OSV, or optical servicing vehicle, um, which carries a robotic arm. Um, Besides the servicing vehicle, the client would also operate with the launcher and also issue which target to chase. Uh, Staark would be associated with the spacecraft. Staark is the robotic arm that is on orbit. And to operate Staark, there would be a robotic arm, which is short for RA, robotic arm operator, and an end effector. Apart from these, we have two other entities or actors. These are rendezvous and proximity operations agent. We'll come to this later in the talk, and mission planner. These are entities who are required in order to execute the mission that we will be demonstrating. Apart from that, the mission planner usually works on navigation products or the required parameters, orbital parameters that are needed in order for the mission to be carried out. And the end effector is basically the tool placed at the tip of the robotic arm in order to manipulate or perform the required activity. Following this, in Capella, the next step would be to list operational capabilities or OCs. These are simply the needs or goals that are required. So it is not just robotics, but our overall overarching goal here is to do these 5 operational capabilities in order to achieve uh, the aim of the mission. So, and the mission is not defined yet, but simply the goals are. And you can see how the relationships between each operational capability and operational entities and actors are defined in this diagram. There are also certain links, like the link between the RA operator and Staark, which are defined as interfaces needed in order to operate the entity. And apart from this, we also use something called as a constraint. So on the palette on the right side, you will see a constraint can be imposed on any operational capability. And this constraint would basically be on the requirements that are needed to be fulfilled. So, for example, provide RPO capability within specified parameters is basically some position and velocity requirements that the satellite needs to maintain in order for it to deploy the arm so that it's close to the target and the robotic arm can operate without the distances being too far away. So this is how we inform the customer that there would be constraints on the system if the customer has specified these at the outset, or while developing the model or the physics thereof, we can impose these constraints on the model itself. Next, we come to the part which is quite important at the operational or need analysis from the customer. So the customer, as well as us, we sit together and we arrive upon a set of operational operational entities, and then we have OAs. So OAs are the operational activities. Operational activities need to be assigned to operational entities or actors. So this is a very good checkpoint during the stage, during the analysis stage in Capella, to know if an operational activity has been defined, but there's no corresponding entity or actor to assign it to. So it would be a good checkpoint to iterate the model and introduce all possible operational activities in order to well define the system later on. If you do not define the operational activity at this point, then and you define the system, it would be very difficult to come back and then change the model. So the impact at the highest level in the Arcadia method is, of course, naturally the highest. So my recommendation would be to iterate the operational model as much as possible. Then we talk about the operational sequence. At this point of time, I'll also open Capella really shortly, but what an operational sequence diagram is essentially is a sequence diagram if you've also followed SysML. So what it does is it introduces dependencies or entry and exit criteria between two operational activities. For example, after launch and separation, what is these operational activities need to be defined in a particular sequence in order for them to be useful to perform the main task. And so we define some additional operational interfaces. For example, early ops slash commissioning is the activity where the satellite, once it reaches the orbit, must enable and switch on the robotic arm, provide power and thermal support, and perform other activities for power and data downlink. Also, in Capella, let me just share another screen and open Capella real quick. Right, so in Capella, it's called the OES diagram or entity scenario. And in this diagram, what is essentially a great feature is if there are more operational exchanges between certain operational states. For example, something else that is happening in real time during an operation, those can be parallelly depicted or shown. So it can not only show you sequences, but also parallel dependencies. And the best part about the OES is you can represent as many sequences as possible. And then those are reflected on the operational structure diagram, which appears in the primary mission architecture that we saw before. So for example, the Staark OSP control feedback is represented here. Then there's another function or feature which is called a loop. So if you remember the constraint that we spoke about on the previous slide, that constraint is modeled as a loop here. So until and unless the RPO function is performed or is maintained, if it does not happen, then there is a loop. So there is no capture happening until that operation occurs. This is a very very essential item to in order to maintain and define the operational sequence for the ConOps. Go back to the presentation now. Right, and then this is the end of the operational analysis stage. After the operational analysis stage, we come to the system definition. So now that the operational capabilities define the system, you can see that we did not define the system till now. That is intentional in the Arcadia method, so that the system evolves during the next stages. Once the operational entities have been defined and the capabilities have been defined, we define a simple primary mission, which is capture target using robotic arm. And the dependent capabilities are then linked to the mission. So we have three primary capabilities, which are directly dependent, and two which are indirectly dependent on the main mission. And all the mission actors that are dependent are also included in this mission capability blank diagram. This diagram is, although might seem simplistic, but when you do top-down analysis, it shows you the dependency, because in the final architecture, all these entities must be present when the system of interest is drawn. Then we come to development of services. So when we go to from the operational viewpoint to the system viewpoint in Capella, the most important thing is introduction of new system entities and system actors, as well as system functions. So this is basically a transition of existing uh, goals or functionalities that are intended from the operational architecture. However, to transition these operational uh, activities to system functions, we need to assign new functions. So new functions are introduced here in green. This is not exactly how it is done in the Arcadia method. However, what we do in the robotic architecture framework is introducing these functions at the system functional data flow diagram, which you're seeing right now. So for example, in order to provide feedback for the current Staark state, what additional capabilities are required are mentioned and identified and added to the diagram. Consequently, once these are updated, um, the system functional chain, which is represented using this red color, is also updated, as you can see. Now, the, the green box is also a part of the system function chain. So using such additional uh, system development or functional analysis techniques, basically, the system functions are propagated through the model, and we arrive at a system structure. So this is the system of interest that you see modeled here, which is called as the robotics servicing system. And you can see all the system actors that were in the previous diagram now captured here. Also included here are 4 functional chains, including the process of commissioning, which we spoke about. So commissioning the robotic arm, that is reaching the orbit, generating power, switching on the robotic arm, reaching the required orbit, of course, and then deploying and calibrating the arm before it does other functions. But the most important functional chain is in purple, as you can see, is to reach the required orbit for the RPO agent to provide the relative solution in order for the satellite to know where to chase the target, enable this transition, and then activate the robotic arm to capture the satellite under the right conditions. And using such diagrams, we inform the customer as to what the system boundary might look like. And it also defines what each individual stakeholder or actor, system actors. Now, these have been transitioned from operational actors to system actors, what individual roles they might have to play. However, the development of the system is mostly within these 3 entities. So, for example, if we need to develop any special system functions in order to make this mission possible or feasible, you can see that there are more system functions that we enable in these 3 entities, which are within the main system of interest. So that is the system viewpoint and how we use the system viewpoint. Let me go back to Capella again to show another thing of interest. So once we come to the system analysis viewpoint, a very interesting, after defining the structure, a very interesting capability that we show to our customer is through the functional scenario. So functional scenario tool, again, very similar to the operational exchange scenario, shows the kind of functional interfaces that are required step by step in order to execute a robotic task. So here we can see that there are about 7 or 8 steps, including some of the functions that we introduced in the last step. And each function between each function from the previous to the next introduces a new data or computational element. And these depend on certain costs for robotics. And this comes to be very useful, as we'll show in the next step. And let's go back to the presentation to see, to get out of Capella a little bit. Maybe this is a, a preliminary required to know what a robotic specification looks like, and this is it is based on the National Architecture Framework. So it's a 6-layer framework, which includes which I developed for the system, which includes interfaces, what kind of sensors the robotic task needs, what kind of motion planning the robotic task might need, what kind of kinematics it needs on board, and what kind of tool action it may need. For the last 4 sensors, for the last 4 layers, we assign a cost. And depending on the sum of each cost, we trade off on each robotic task. So robotic task, if it uses certain sensors or certain motion solvers, may be more complex or less. And this also is of interest to our customers. So we use an add-on tool for this in Capella, which is called as the PVMT or a PV editor. This tool is used to create a domain, a properties value domain, where we define uh, a couple of enumerations and then assign these enumerations or properties certain values based on how they're defined. For example, for sensing, if we're carrying only encoders, only an incremental encoder or both incremental or absolute encoders, or some visual cameras or depth cameras, we assign a specific value between 0 and 1. Similarly, for planners, based on the relative complexity, computational cost and complexity of the planners, we assign a value. And thus, we achieve a quantitative trade-off based on the sum of these last 4 layers, which are sensing, planner, motion manipulation, and tool action. So, for example, what we just saw in one instance, we assigned for the customer sensing in this particular robotic task through an incremental encoder only. So you can see that we assigned a sensing cost of 0.1. These costs are normalized costs between 0 and 1, and they're based on relative complexity or difficulty. The planner is also assigned for this function, so this totals up to give us a sum. And in the second instance, we have the customer requesting us for a more complex but robust solution to, in order to find or acquire their target in the lack of visible light. So there we use the depth camera, so a time of flight camera, and of course that increased the sensing cost from 0.1 to 0.45. Similarly, the planner was upgraded for a more robust solution, which also increased the planner cost. So relatively, the first scenario had a cost of robotic cost of 1.5, whereas scenario 2 had a total robotic cost of 2, which are the sum of these individual scores. So tools like these allow the customers to know not just how the robotic architecture is built, but what goes into each element. And the PVMT add-on from Thales is a very useful tool for us in this case. Last but not the least, in conclusion, we saw that Capella helped us reduce our overall modeling effort for case studies of Staark, because Staark is an already developed space component, so we don't use Capella to define the physical and logical architecture. However, in robotic architecture studies, it helps us explain to the customers how Staark would fit into their uh, existing system or a new system that we define. Capella also helped us in architecture analysis, as we saw in the last few slides, versus traditional methods by almost 60% using tools such as PVMT. And Capella sometimes also has a very uh, dominoes effect on describing system of systems like frameworks. So when we need to share these architectures, these are easily shareable. Apart from this, overall, I think model-based systems engineering in defining architectures is fairly important and plays a critical role in well-defining orbital servicing platforms and missions. So I would like to end, first of all, thank all of you for your interest and attention, and I'd like to thank Redwire Space Europe as well as Obeo and Thales for making this talk possible. Thank you very much.
Okay, thank you very much, Vinayak, for the presentation. Now, let's see if we have some questions. In your operational entities, you have included Staark as an OE. How does that align with Arcadia's operational analysis layer, where you're not supposed to introduce the system yet, and why did you choose to do so?
Correct. It might look like Staark is an system, but Staark itself is not the system. The system of interest in this case was Staark as well as the spacecraft, the OSV, and the operator. So it's a different approach. Of course, Staark is an already well-defined component or module, so I would treat it as a plug and play drop in into any architecture. And if architecture can allow me to do that, it saves us time as well as definition.
So, next question. Can you give us a rough idea of the size of the team working on that project and how many systems engineer worked on it, etc., for instance?
Sure. I think this was a fairly small team. So there were two people working on it. Both system engineers worked on it. So myself and another junior systems engineer. And it took us more time, but these were used for studies where we needed to define external interfaces. So it did not require too many people because uh, we were defining architectures, but we needed people with certain expertise. So we had more full-time engineering effort on the kind of talent we wanted to execute this modeling rather than the number of people. So yeah, not a big team, surprisingly.
Now, next question by Pascal. So, your system level really looks like a logical architecture one. In Arcadia, the system is a black box. Yeah, maybe you have some comments you can do on that remark.
Sure. Yeah, it does look like a logical architecture. However, there are certain exchanges that the operational layer allows us to. One could actually take it to the logical architecture level as well. However, our intent is to do several iterations at the system layer in Arcadia, because if you were to iterate on the logical architecture model, um, there are fewer physical architectures possible. I don't know if that makes sense, but here we work with certain constraints on modeling systems and interfaces in space. Some are defined, very well defined, so you cannot change those components or categories. But yeah, there is probably another um, uh, process in modeling this. This is just one of the several processes which seemed fair to us. But I'm sure we can also extend it to the logical architecture, but it would become more constrained.
Next question. The the OCs as defined seems to have intimate knowledge of the system, which is yet to be defined. This is not the speed of Arcadia for the OA step. What's your rationale on these OC choices, which seem to be close to the system functions? I think it kind of yeah, except if you have something to add, but it's kind of similar to the previous one. Um,
Yeah, yeah, I think that is quite similar. But yeah, I can add that the OCs were broad, quite broad, and as you saw, the system functions which were added on later were very specific to robotics. So although there were some OCs which were similar to system functions, not OCs but OAs, I think that's what you meant. But the OC choices were quite broad. There were only 5 OCs, but the OAs were closer to system functions or parallels because they involved an automated transition using uh, the the tool. And yeah, it could be modeled with a different system function name. However, we saw that we wanted to fill in more depth at the system functional architecture level. And that's why we paid more attention to this, and that's hence the choice.
yeah. When you perform trade-offs analysis, is there a way to show graphically the performance cost evaluation to see Pareto fronts, for instance?
Well, that's a great question. So we basically use Python for Capella to do this. That we just basically summing, but I think that's even a better performance cost metric to show graphical. I mean, like a Pareto logic or a spider web evaluation that can be done based on the relative cost. But I think we make it more open because complexity in robotics is very relative, especially the computational complexity. So we wanted to baseline it, and once you baseline it, I think for Pareto logic to be implied there would need some sort of non-baseline benchmark, but it's something we could look into in the future.
Mhm. Thank you. Yeah, we still have some more time. So next question about mission capability in system analysis. How and why do you integrate the phases about developing efforts, commissioning project, etc., and system activities?
Okay, so
Yeah.
if I understood the question, so the phases that are mentioned here are the OCs and the system activities. So yeah, if I mean if the question is to evaluate mission capability, I think it has to be done at the mission blank diagram. So there are no system functions or system activities there. However, if you try and trace back using the Capella approach and ask how each capability is fulfilled, you could take a look at the system allocation diagrams. So the system activities, all of them reach target, provide feedback, basically will be allocated to operational or a system activity and the activity to the mission through the capability. So that's as simple as that sounds. Um, that's the method we used or the logic rationale we used while developing the model.
Mm-hmm. Thank you. Any reason to have the Staark as unique component of OSV? And same question for having parent OE allocating activities.
Yeah, this is a modeling choice, of course. Reason for Staark being a unique component of OSV is because Staark is already fully developed. So we wanted to use it as a drop-in, like a plug and play, and there are interfaces between the OSV and Staark. At the operational level also, the OSV is the one through which Staark is operated. And while we're not defining the system, this was a modeling choice based on the, let's say, the physical setup of the robotic arm and the servicer. It is indeed a element. If you look at the product breakdown structure, it would be Staark under OSV. So we followed the same rationale, and the same answer goes for other OE activities. For example, Staark having other actors. But yeah, that's mostly the thinking behind Staark as a sub OE of the OSV.